Thank you for having me. I will be talking about the brief history of virtual threads in Java at the JavaDay Lviv, or Lvov, how we say in Czechia. And I will start so we don't waste any time. I have a lot of slides for you. So first, a little bit about me. My name is Daniel Katz. I work in Oracle as a Java developer. I work on the project Helidon. You can find me or various social networks like Twitter and Blue Sky and Mastodon and all the others. There's so many of them nowadays. I'm also blogging sometimes. You can find most of my articles on Medium. What's the agenda? We have pretty wide agenda for this talk. We will start with the virtual threads. I won't be describing what the virtual threads are that much because you already heard that in every other talk about virtual threads already. So instead of that, we will take a look at some cool optimizations or tricks the virtual threads are doing behind the scenes and what makes them so cool. Then we will take a look at the timeline of Java concurrency to see, a little context of the things in concurrency in Java. We will do some time travel to see the green threads, which have been part of the Java years ago. We will play with them a little and try them out. Then we will switch to the operating system threads abstraction. Take a look how we have worked with them for so many years, and then we will switch nicely to reactive Java to solve some issues we had with the platform threads. We will take a look at some advantages and disadvantages there. And then there will be a shameless plug from my project or our project Helidon. We will take a look how we leverage the virtual threads in the Helidon, how much it helped us, and what we have achieved with that. And at the end, if we have a time, we will take a look at Achilles heel of virtual threads. It's not such a scary Achilles heel anymore after the JDK 24 release, but we will get there hopefully in time. So this is the agenda and we can start. So the virtual threads, the blocking is cool again in Java. Finally, we have coroutines in Java, basically delimited continuations. You can choose to create a virtual user threads instead of the physical ones. It is way cheaper, so you can make millions of them. There is no pooling needed, and blocking is completely fine. Naive imperative coding style is safe with performance comparable with to reactive constructs. Work scheduling is done in JVM, avoiding the expensive context switching on operating system level. And we are saving all that off-heap memory otherwise allocated for physical threads. And how does that work? Let's look inside the JavaLang thread class. This is a screenshot from the source code of OpenJDK right before release of JDK 21. It changed a little nowadays, so it's not the same, but the trick is still the same. It's been more obvious back then, so that's why I'm using this screenshot. You can also see the blame here that it's been done by Alan Bateman, that's one of the guys behind the Loom project. So those super clever guys who are responsible for this super cool feature. If you will take a look at the sleep method in the JavaLang thread class, you can see that something completely different will happen for the sleep if we are running it on top of the virtual thread. And if you will follow the rabbit a little deeper down the hole into the sleep nanos, we will get into the virtual threads class, and we will continue into Park Nanos. We will find a method which is called yield continuation, and that's the kind of a proof that those are actually a continuations under the hood. It's just the API for this continuation cooperation is cleverly hidden, so we cannot really use it manually. But instead of us, it's used by the JDK itself. So when you sleep your thread, it will actually yield continuation, and all the cool stuff will happen also when you block somewhere and wait for something. I won't show you the diagrams with a million arrows. You already saw all those pictures, I guess. Instead, I will show you how it looks in your IDE. So this is a screenshot from my IntelliJ IDE, and I have stopped my debugger here on some virtual thread. And you can see that you can have millions of virtual threads, obviously, on top of a few carrier threads. But in my case here, I had only one virtual thread, so it's very simple. While I have a lot of carrier threads, the thing is that the for join pool is a scheduler for the virtual threads. So all those worker threads in the for join pool, those physical ones, we are trying to keep at some smaller number and use them really effectively. It's called from the point of view of the virtual threads as carrier threads, and because they are kind of carrying the virtual threads we are actually using from our point of view. Again, the virtual threads are scheduled over a bunch of physical carrier threads. Everyone who at least heard about virtual threads already knows that. The scheduler is a marvelous and battle-proven piece of engineering we have in Java for quite some time already. We will see that on the nice timeline later. You can see it yourself when you are debugging like that. That's what actually is happening behind the scenes. And here is the final proof. If you poke around a little more through the OpenJDK GitHub repo, you can find that the default scheduler is actually a fortune pool. Here you can see it being set up. So that's the only available scheduler right now, but it doesn't mean it's a bad scheduler. It's actually a really good one. We will get to that later. More interesting thing is mounting and unmounting. You know, the process when we are switching the virtual threads on top of the carrier threads, how it's being done. We are actually calling that freezing and thawing. So when continuation is being unmounted from the carrier thread, the continuation part of the stack is being saved for later. We call that process freezing. And when continuation is mounted on carrier thread back on, its stack is being copied on top of the carrier thread stack. We call that process thawing. So I have prepared this small animation. I hope it will work. So we can try to demonstrate the stack manipulation with a small server example. When virtual thread gets blocked on the read socket method, so we, as most of the server, we are running this endless loop here. And when we are reading the socket, we are blocking until more data comes over the socket. So that will be the time when there will be little if somewhere, which will yield to the continuation. So the carrier thread is freed. And the stack of our virtual thread is saved for later when the data actually arrive over the socket. So we will take a look at what will happen. It will nicely animate. So we can see that we have moved the part of the stack which is related only to the virtual thread from the carrier thread and saved it somewhere for later. And the carrier thread is ready to serve some another from those millions of virtual threads we can run, right? And it's being saved for later when it's mounted again. Then, when the continuation gets mounted again, it's not that the whole stack is copied back, but just a few frames with a return barrier. And it's pretty cool thing. The return barrier is a lazy substitution which guards the return addresses of read socket. methods, in our case, like that. So we can see that we don't have to move around the whole stack of the virtual thread. So we are not like in the operating system case. We are not moving the whole stack of the thread. We are moving only the part. I will show it in camera. Only the part of the stack which is related to the virtual thread only. The rest stays with the carrier thread, and we are saving it for later. And even though we are not moving all around, because as you can see in our example, we are moving in this example endless loop. The actual number of frames is only those which are, starting from the loop deeper. So we don't need to move everything, to the start server methods and so on. So instead of that, when the barrier is reached, we will load that one more stack when we need it. And we don't have to move around the rest. It will stay hidden or for later when we need it. But while we are looping in this endless loop, we don't have to move around this stuck chain, how it is called internally, around. But instead, we will move only the part which is relevant to our live code. This way, we are saving a lot of performance here, and it's not. That's why the virtual threads are so effective and performant. And it's not the only super cool optimizations. There is more of them, like the stack chunks which stays saved for later. They can be compressed, so they take less memory. That's why you can have millions of virtual threads. And it's all happening on the garbage collector threads, so all the contention is acceptable. So there are really cool features inside the virtual threads, which enables them to be so performant, which you can discover. And if you want to know more, there is a really cool video on YouTube from Ron Pressler. It's called "Continuations Under the Cover." Under the covers, he explains the stuff way more in detail because he actually understands them. And if you want to know more, I can only send you in that direction. But that's why they are so cool. Now it's time for some history. Let's put some of the important Java concurrency events on the timeline so we can see the context a little better. So here is the timeline. If you look at it, this is the 30 years of Java, right? And you can see that out of those 30 years of Java, we didn't have the virtual threads for so long. If you look at the right upper corner, no, here, yeah, I'm merged. Okay, this way, you can see that that's approximately the time when we are using the virtual threads. On the left upper corner, you can see the time when we had the green threads in Java. We will get to it shortly, what it is and how it worked. That was a kind of user threads we already had. And we dropped them in JDK 1.3. So since 2000, we don't have them. And we have been using native thread abstraction only in Java. And if you look at the timeline, it kind of looks like nothing has been happening. It hasn't been happening much in the concurrency timeline in between, but that's not really true. We can add some cool stuff which has been happening. So you can see that in the same year when the green threads have been dropped off or ditched in 2000, the Doug Lee himself published his paper about fork join scheduling in the very same year. He was already proposing a different way how to schedule concurrent tasks directly in Java. And many others were trying to figure out the way forward. Like in 2008, the Matthias Mann released his continuation library. In 2009, there is this paper, Lazy Continuations from Java Virtual Machines. It's been authored by Lukas Stadler and Thomas Wentinger. If those names seems familiar to you, those are the guys behind the Graal VM nowadays. So some really clever people have been thinking about this back then. Then there was a release of JDK 7, the last one with the code name. It was Dolphin was the last one. Since then, the JDK releases don't have the code names. with which we got the for-join pool, and the for-join pool has been actually implemented and delivered by Doug Lee himself. So thank you, Doug Lee, for inventing the stuff and give it to us. The for-join pool is basically not only a scheduler, is a framework for delimited continuations, but you have to drive the tasks yourself, and it can be the API can be quite complicated to use. In 2012, there was a Go 1.0 release with Go routines inspired by Erlang, and proves that delimited continuations are really, really cool. In 2013, Ron Pressler releases his first version of his Quasar library. That's a lightweight threads inspired by Erlang, Go, and Matthias Mann's library. And that time he was working on some kind of concurrent in-memory database, and his customers didn't want to use async code. Obviously, who would want to, right? So he created his own version of continuations for Java. In 2014, asynchronous programming in Java gets way more friendlier with David Carnock's RxJava. So that's kind of a peak of the reactive programming, because we have really cool operators and we can actually manage the asynchronous programming a little better. All those callback hell isn't that unbearable anymore, but still, yeah. In 2017, the Kotlin has coroutines, but more importantly, Ron Pressler is joining Oracle to work on adding continuations and fibers to JVM. That was the original name of the effort. He joins Alan Bateman and all the other cool guys, and the project Looms gets in motion. And then it gets faster. We get first preview in 2022, and with JDK 21, we finally get the virtual threads, and it really fits nicely with the legacy threading API in Java. Everything is scheduled by battle-proven Doug Lee's for-join pool. So again, thank you, Doug Lee. You are our demigod of concurrency in Java. It's not only the for-join pool. If you look in the Java concurrency package in Java, you can actually see that his name is almost everywhere. And yes, he's on the book, on the famous book with trains, right? So most of us who has been trying to learn the concurrency in Java have read this book for sure. So that's our hero here. Now, a little recap. Virtual threads are user threads in Java. They are scheduled by Mighty for-join pool. They are inspired by Erlang, Go, and Quasar. It's many-to-many model, so many carriers are powering the many user threads. And how is it similar to the green threads? We will get there. But for that, we have to travel back in time. We have to travel back in time in 1997. And why into the 1997? Well, because it was pretty cool year, right? The Bruce Willis still has hair. Max Verstappen is born, and Sun's CEO Scott McNealy is on the cover of Fortune magazine dressed as a Java man. So that's a pretty exciting year, I would say. And also, in 1997, that was the already out Java 1.1, which is the earliest and easiest JDK you can try with green threads on nowadays. So it's more of a pragmatical reason, at least for me. All you need to do is download the latest Solaris and run one of the 1.1s downloaded from our archives. Oracle has really cool archives of old JDKs, but it's not like they are all of them. So the earliest one with the green threads you can find there is for the Solaris, and it's 1.1. That's why. Just be careful that not all the archives there are complete with both green threads and native support for you, because back then, we will get to it. Back then, the JDK was kind of like a puzzle with a lot of pieces, and when you didn't need something, you didn't have it in your archive or installed at all. And we will explain it right now. So the first thing you can notice on this really old Java is that in the bin folder, the Java executable is in fact is not a binary. It's a Korn shell script which gets together the right bits of your JVM based on the architecture and selected threading model. So you can see that there are two options. There is green and native. The green is the default, and then it puts together the right libraries for your running JVM. But first, let me take a step back and ask Wikipedia, what is the green thread? The answer is that it's a user thread scheduled by JVM instead of the operating system. So again, we are hearing the same again, like with the virtual threads. Important part is the claim that it emulates multi-threaded environment. And that's the difference. That's the big difference from the virtual threads. Green threads are many-to-one model. It only emulates multi-threading. We also already have had many-to-many model. It was similar to modern day virtual threads, but the magic happened in the native Solaris threads library, which has been later replaced by POSIX threads. So it haven't been there anymore. And it wasn't so performant as the virtual threads are nowadays, obviously. So let's give it a spin. We have traveled back in time to play with the green threads. So we will give those emulated multi-threading a ride. For example, this example runs 3 threads, and we will let them sleep in parallel, so we can actually see the concurrency in action, right? So we will sleep for 300 milliseconds, 200 and 100, and we should see how they are overlapping each other. So first thread should stop way after the second thread started, and so on. So when we try that, we can see that with the native threads on the left, you can see that it seems pretty much concurrent, because it is, right? So it's actually starting all 3 threads and then it's stopping. On the right, you can with the green threads, you can see that it seems fairly similar. It's starting 3 threads and then it's stopping 3 threads. So it seems to be they are overlapping really nicely. So that's a really good emulation. You fooled me enough. Now, let's make it a little harder. This time, no sleeping. We are going to abstract the thread with some actual work and pin the thread down so no one else can use our thread. Someone should be screaming right now, oh, come on, there will be the loop unrolling optimization and this won't pin thread at all. Well, remember, we are in JDK 1.1, so there is no loop in the unrolling optimization, and this will pretty much pin the thread very safely. So here are the differences. You can see that the native threads, again, they are pretty much overlapping. You can see that they are starting, then ending. So that's pretty much in parallel. With green threads, you can see that it's not parallel at all. It's actually the first thread needs to stop before the second starts, because it's running on top of the single thread. It's just emulating the concurrency, so it's not really concurrent, and it never overlaps. And as you can see at the bottom, the green threads have been default. So if you run it, our example run on default setting, you will see that that it's actually not being parallel, kind of like a Python nowadays, right? So this is what how the green threads worked. Here is a really nice diagram from the Solaris documentation. You can see how the mapping looked, that we are actually multiplexing over a single lightweight process or physical thread, how we call it from our side of the JDK. And this can be good enough on single CPU machines. Actually, it's been pretty cool, but the times are changing and computers have been changing, and the computers are having more and more CPUs. So this was really not the optimal setup for our concurrency building blocks. To substantially increase application performance. Now I'm citing the actual reason why green threads are replaced by physical threads abstraction in 2000. So that's the reason why we don't have anymore. It's been only emulating concurrency, and that's why we don't have them We can compare it with the other cool diagrams from the really nice Solaris documentation. You can see that one-to-one mapping is what we have been using for 20 or so or something years in Java. So with each Java thread, we have been actually starting new physical thread, and that can be quite expensive. We will get to that. And also the many-to-many with Solaris Threads library. It was very interesting. It's just also have been replaced by POSIX Threads API on the C level, and then we know the history. And what is left of green threads in Java 24? The green flag is still there. You can actually try it, and it will only print out that it doesn't support green threads anymore. It's kind of sad. There was some bits of logic left over a few versions back, but I saw that with virtual thread implementation, Alan Bateman have cleaned up that bits already. So only left over after the green threads is this one little flag, which is still there. You can try it out yourself. And we are stuck with physical threads abstraction since 2000. And it's kind of okay, because JVM spec doesn't actually state how Java thread should be mapped to operating system thread. So it worked really nicely. That's why we had the flags, and we have been able to switch from one to the other. One-to-one model, the physical thread abstraction have some problems, quite some. For example, starting the kernel thread is really, really expensive. Every kernel thread created by JVM needs megabytes of memory. The context switching on the operating system level is very, very expensive, and it gets even more expensive with more threads already started. So it gets worse as you're starting more and more threads. So what we have been doing about it, we have been creating a thread pools to avoid starting too many of them. We have been reusing the threads, to avoid the expensive thread start. We have been trying to avoid blocking of the thread to minimize the expensive context switches, because operating system doesn't know anything about how the data are structured in our use case on our JVM. So it just moves around the whole stack with all those megabytes of data from one cache to the other, and it's really, really expensive. So we have been avoiding that. We have been avoiding blocking by keeping rather the really small amount of the threads really busy, and by organizing the tasks for them in such a way no blocking is needed. So we have been actually scheduling the work ourselves, right? So how have we been doing that with reactive programming? That's the way how to avoid blocking, thus avoiding the context switches. And to do that, the code needs to be asynchronous. Don't let your thread wait for something. Continue to work on something else. A response or result will come by callback on someone else's thread. It means that instead of blocking, you just provide a callback function. But by ditching the blocking, we have lost natural back pressure. We can't control how much data comes back on the callbacks. So everything gets way more complicated. The callbacks are executed on different threads. No one is waiting for anything. The order of execution, well, there is no order of execution. Actually, all those race conditions are just waiting to happen. But luckily, we have reactive streams operators for callback orchestration. So reactive operators are an implementation of Reactive Streams API, which is the set of APIs for orchestration of callbacks, surprisingly, with built-in back pressure mechanism. It was an attempt to bring order to the callback hell by a set of very strict rules, and is even part of the JDK since Java 9. You can find it in JavaUtil concurrent package in the flow class. And but while the interfaces seems to be really simple, for the specification rules are ridiculously complicated. So they are actually so complicated that when you try to implement the interfaces yourself, your IntelliJ IDE will warn you off. Don't implement it yourself. This is actually a screenshot from my IntelliJ. Instead, there are existing libraries providing reactive primitives, really famous and good ones, with operators implementing reactive streams in some builder-like patterns usually. So you can use Eric's Java, that's like the most famous one from David Carnock and a bunch of Netflix guys. There is Reactor from Spring, also co-authored by David Carnock. There are Akka streams for any Scala people out there. The service talk from Apple is a really good one. We have in Helidon, we have our own operators. They have been also contributed by David Carnock. And Mutiny, that's really nice one from Quarkus and Red Hat. That one is a little different. It has very interesting context-aware builder pattern, if I can say so. So there is a lot of them out there. You can choose yourself which one you want to use. They are using common APIs, so you can connect them together. But still, it makes things easier. But still, it's still a trap. The reactive programming has a very steep learning curve. It's a maintenance nightmare. The debugging is really hard. The stack traces are practically useless. The blocking or abstracting code needs to be offloaded to extra threads anyway, because you cannot block anywhere. It has disastrous consequences. So don't. There has to be something better. And remember, the reactive APIs are viral. Once you use them, you have to propagate it further to avoid blocking. So it infects all your code base, and it's really hard to get rid of it. Trust me, we did that in Helidon. It's hard. So now let's talk about Helidon, my shameless plug. It's a project I'm working on, so it's obvious. I will do a short introduction and show you how we use the virtual threads. What it is and how we switch from the reactive APIs to blocking ones with the virtual threads. So what it is, it's a microservice framework. To describe it best, our main competitor is a Spring Boot. So that's the easiest way how to describe it. It's a web server. It's built to play really nice with Kubernetes. It's completely open source. All source code is available on GitHub. Even though we are backed by Oracle, it's completely open source. You can use it for free. Unlike Spring Boot, Helidon keeps the number of third-party dependencies as low as possible. This is very important for corporate users, as getting the approval for third-party library can be complicated in larger companies. Trust me, we know something about that. And you don't want to download half of the universe, just to print out the hello world, right? So that's the Helidon. Here are the examples. We have two flavors of Helidon, which you can use. We have Helidon SE and Helidon MP. Helidon SE is a micro framework. There is no magic, no injection, or in the later version, we have some build time injection, which has same performance, but that's out of the scope of this presentation. It's a really interesting feature. I invite you to discover more about it. Again, Helidon SE is a pure performance. You get it together with builders or lambdas or those build time annotations, but that's something else. And there is another flavor, the Helidon MP, and that is quite opposite. It's annotation driven. It's full implementation of CDI and JAX-RS. We implement the whole microprofile specification, and it's very easy to use. So if you ever used WebLogic, the Glassfish, Wildfly, WebSphere, you know how the JAX-RS endpoints looks like, and you can port your application really easily there because we are implementing the same spec. Of course, the latest and most modern version of it. Here is the comparison between Helidon SE and MP. Helidon SE is the builder pattern, so you can see that we are doing little hello world with HTTP GET endpoint or resource. I say resource, the Spring developer would say controller. On the left side, you can see Helidon SE builder pattern with Lambda, and on the right, the JAX-RS resource with annotations. So you can choose your way with Helidon. And what we did in Helidon, you can see that between Helidon 3 and Helidon 4, we did a big change. We have actually ditched Netty, which is really cool library, one of the fastest and best ones for working with sockets asynchronously in Java. The problem is we didn't want to work asynchronously with anything anymore. We wanted to use virtual threads because it's the same trick, you know, under the hood. So we have removed the netty and created our own brand new in-house web server with secret code name Nima, which is clean, fast, and optimized for virtual threads from the ground up. So there is no nuclear power plant with asynchronous and reactive APIs. We have really nice, clean, and small and simple web server to maintain, because everything gets way simpler when you get rid of the reactive APIs. And the blocking is embraced even in Helidon SE, so it's not reactive anymore. How does it look? You can see the difference between Helidon 3 and 4. You can see it best between the Helidon 3 and 4 SE, because SE have been reactive. So all those reactive APIs has actually infected our APIs. So as you can see, if you wanted to call from your endpoint another endpoint with HTTP client, you had to use reactive one. So on the left side, you can see old Helidon 3. And with reactive operators, we are actually calling another service. With callback, we are responding to our own client when we get the response. So that there is a callback in for single. We are doing some business to uppercase, very clever one, right? And we are also tending for errors with special callback for on error and so on. So it's hard to explain to that new junior developer joining your company, for sure, right? When you debug it, you are not going from up to down. We are jumping, you know, from callback to the callback, because there is no order of things. The stack traces are kind of very complicated, almost unusable. So debugging it, maintaining it, explaining it to anyone, or even remembering what have you done last year in this corner of your project can be quite challenging. While in Helidon 4, the same code is blocking and imperative. You can see that we are using blocking client now, and we just request our data. We get the response. When we get the response, we do our business, and then we send the response. So it's imperative. The order of things is up to down. You can jump over it with the debugger really easily. It's easy to reason about, it's easy to debug, it's easy to maintain, and you can actually explain it to that intern developer who just joined your company. So that's the main difference when you switch from the reactive APIs to the virtual threads. And performance is almost on par, so why would you stay with the complicated stuff? The problem with the reactive APIs is that nobody does them right anyway. So in the real world, you usually get slowed down by someone committing something unthinkable in reactive way of doing things. Here is another timeline. You can see how it went with Helidon. We have been working on our virtual thread-based web server in advance, so you can see that we have released Helidon 4 right after the JDK 21 have been released. It's also the minimal version you need for running Helidon 4, because it's based on top of the virtual threads. And how we differ from our competitors. Our web server is built and tuned specifically for virtual threads. You can't just turn off the virtual threads in Helidon. It's not possible. There is no switch for that. It's not hacked in. It's just wouldn't work with physical threads anymore, because it's optimized quite differently. All those contentions are very different with virtual threads. The pooling is destructive for the performance with virtual threads. So we have rewritten everything. It's super simple now, easy to maintain. It's really nice and clean web server we are working with right now. Work with sockets is specifically tuned for virtual threads. We have worked on that in close collaboration with Loom developers. Other frameworks support the virtual threads usually by offloading to them from reactive APIs. So you have kind of both worlds there. But, you know, with those two abstractions layered over each other, you are always losing some performance. And it's even less maintainable because everything is super complicated. like this. You can see that in our world we are going from the imperative web server to imperative handlers, so everything is super easy. If you are running on the runtime which is reactive and just offloading to the virtual threads, you have kind of worst of the both worlds. So that's why we call it big win, that we have the really simple and easily to maintain web server in Helidon. And now we have some time for the bonus part. That's the pinning. I hope we have some time. Maybe if you can wave at, I don't see you. If you can wave at me if I have a time. I guess I do. Nobody's complaining.
Yeah, we still have a time.
I can hear you. Awesome. So I will continue with pinning.
Definitely.
What is the pinning? I have draw a really nice picture. It's like the peak of my graphic capabilities. So the pinning is a situation when your virtual thread is reaching somewhere where the underlying carrier thread can be blocked together with the pinning. So there is not that there isn't that clever logic if you are on virtual threads yield instead of block. This can happen, for example, if you are calling something through JNI interface and there is some mutex in your native library, you cannot really avoid that, right? So if your virtual thread is being blocked, then you never got your carrier thread back into the pool and it won't be available for another virtual threads. So it doesn't break everything, it will just degrade your performance a little. And we can take a look what to do with that. Usual suspect was, I'm saying was, synchronize. It wasn't always harmful. It was fixed with JDK 24, so the synchronize isn't really a big problem now for the virtual threads. And short-lived in-memory operations weren't harmful at all even before that. In case of pinning, the carrier thread pool compensates by spinning additional carrier threads, so it leads to performance degradation, but it still works. That's important. And for example, rand log has been always virtual thread friendly. So we will take a look at some example. This example I'm doing on JDK 21 because on 24 it wouldn't work because it's fixed already. So I'm using synchronize here and I'm doing some sleeping inside so I can simulate the pinning. We have discovered a few slides back that sleep is actually yielding continuation on the virtual thread, but this time the blocking happens in synchronized, so there is no alternative logic for virtual threads available and we just cannot enter the block anymore. So we have two options how to detect the pinning here. The first option for pinning detection is with JDK trace pin threads property. It's very easy to use, kind of tempting to use it all the time. You can exactly see where the pinning happened on the printing stack trace. You can tweak it a little with properties. You can set the property to short, so only the problematic frames are printed and so on. This approach is not recommended for production use with Helidon, definitely. The printing to system out with this type of contention can be quite problematic. As you know, the printing to the system console in Java is actually synchronized, so you don't really want to do that. Also, there was a really nasty bug. I think it's already fixed. There was really ugly deadlock which happened from time to time. So instead of that, there is much better way how to detect pinning. And that's a special flight JFR event, JDK virtual thread pinned. It's very easy to use as it is enabled by default for operations that takes longer than 20 milliseconds. The 20 milliseconds is kind of like agreed time after which we are considering a carrier thread as pinned. Until the lifetime is under 20 milliseconds when we are somewhere, it's considered not pinned, and after 20, you can change that usually with this pin detection, but 20 milliseconds is kind of agreed on as the right time frame. We can enable it explicitly in our example and dump JFR recording like I did here to extra file and read it later. In the recording, we can find the very same information again about where the pinning crime have been committed. So we can see it's on line 6 in the main method. And of course, in Helidon, we also have those GFR events leveraged in our JUnit extension. So if you are testing with Helidon, you can turn on the pinning detection, and your test can actually fail in case you are doing something dangerous with pinning. How to fix that? Well, obviously, if you upgrade to JDK24, you will fix like 99.99% of pinning issues, because the monitor issue with the monitor in Java has been fixed. So the synchronized for is now virtual thread friendly. To fix that, otherwise, if you have to stay on JDK21 for some reason, fixing the implementation to the virtual thread friendly reentrant lock will help always. You can, if it doesn't work for you, if you are using some native library or having some task which has high CPU usage, so the virtual thread wouldn't help there anyway. If you are mining by bitcoins or something, then you can always offload to the new physical thread. So that we have some cool features for that in Helidon too. That's by the way, that's the same thing you would do in reactive code, right? If you have a blocking code on something very CPU intensive, you just have to offload to another thread anyway. Plus, you have to respond on the callback. This doesn't really happen in Helidon. As you can see, in Helidon MP, we have few annotations for that. You can use jersey manage async. You just place it on Jaxares resource, and it will be run on the physical thread. You can use our own annotation, execute on, that works even on CDI beans, and then you can configure the thread pools and everything in Helidon configuration. It's also really powerful tool. In Helidon SE, you have to get your hands a little dirty, because that's for the guys who want to, touch the performance themselves. Here I have used our thread pool supplier, so it supports the security context and stuff like that. But as you can see, even if I offload it here to the physical thread, unlike in the reactive code, I don't have to use a callback to return from that. I can just block the virtual threads until the physical thread is done. And because of the clever scheduling behind the scenes, I don't have to take care about it anymore. So it's even easier than offloading in the reactive APIs. And this is very old slide. This is from pre-JDK24 release, where I have been explaining that a lot of libraries are already virtual thread friendly, like MySQL driver and Oracle driver, Mongo driver. Everyone is replacing synchronized with virtual threads. But the thing is that with the release of JDK24, we don't have to do that anymore, because synchronize is virtual thread friendly now. So future is now, and the pinning isn't that scarecrow anymore. And there's a proof. I have run our reproducer on JDK24, and you can see that that pinning crime doesn't happen anymore. Remember, in comparison with accidental blocking in reactive code, the pinning suddenly doesn't look that bad. It's not disastrous. Your server will still work. Your performance will degrade a little. If you block in your reactive web server, it will very quickly become unresponsive or something even worse. So the pinning was a scarecrow. It's not anymore, and even so, it wasn't that dangerous as blocking in the reactive handlers before. And that's all from me. I hope you like the way we have put the virtual threads in action with Helidon. I hope you liked my small history lesson. If you have some questions, now is the time. I will gladly respond to them.
Thanks a lot, Daniel. Yeah, that was a great history, starting from the early days of virtual threads. Oh, no, it was green threads. Yeah, it was really entertaining and interesting to understand, and even to know that it has such a rich history. It's not just a recent feature. How long does it take to implement some stable feature? Pretty interesting. Thanks a lot for all these insights and details of virtual threads. And yeah, we have bunch of questions. So let's start our Q&A session. And the first, well, pretty long question. The first question from Frankie DeJong. Interesting name. And yeah. Okay, I'll read it. So, Daniel, considering your work on Helidon and its reactive foundations, how do you envision virtual threads reshaping the trade-offs between reactive programming and traditional imperative models? And do you foresee a future where frameworks like Helidon might learn more heavily on structured concurrency rather than reactive streams, now that the performance gap is closing?
The thing is with performance gap is that theoretically, with really properly done reactive coded web server, you should be, at least that's from my side how I see it, you should be actually able to achieve slightly higher performance than with virtual threads, because there is always some performance with that artificial scheduling, right?
Mhm.
But the thing is that I have been supporting reactive web server for a long time, and I can tell you that I have never seen the reactive code used properly anywhere. It's always done badly, and just small mistake can mean like dramatic performance degradation in your code with reactive code base. So I think the simplicity of imperative coding is the added feature. The structured concurrency is really nice. I think the Java deserves APIs like that, because it will even further simplify those things. It won't be that interesting for Helidon as it is for other users, because we are doing a little different things inside our runtime. So we will definitely use it. But the structured concurrency as a feature is part of the Loom project. It's just not that important for us because we are behind our own API. We will, of course, make those APIs work really nicely with all the new features in Java, as we are always keeping ourselves on the edge. But the structured concurrency isn't really like the main important things. The main important thing for us was that we could escape for this clutch of the reactive. How do you say it?
Callback health.
Yeah, callback health. Exactly. That's the thing, because the whole code base is really complicated, and maintaining the project, which is that big and reactive, is quite challenging. And from our own view, that switching to the imperative coding in our web server made our life so much easier, and we can concentrate on new features. We can fix bugs way faster, because everything got so clean and nice. So I hope this will kind of go further, right? There's still place for the reactive coding, like for messaging and asynchronous communication. There is always a place for reactive APIs, but hopefully it will be used only when necessary, and not always just for sake of some artificial performance which didn't ever happen anywhere.
Yeah, agree. It won't gone. It will still have its own area as everything. Yeah, it's true.
Exactly.
And thanks a lot, for answering this question. And we have next one from Mr. Mike. He's wondering, why were green threads originally abandoned in favor of native threads?
Because it's been emulating the parallelism on top of the single thread, right? That's kind of like on the in the Python you have this GIL lock, right? So if you are actually running only on one thread all the time, it was the same thing. They've been only making it look like it's concurrent, but it wasn't, and it was okay on those single CPU computers, because it made sense. You had only one CPU anyway, so why would you play for the real concurrency? But nowadays we have like hundreds of cores in servers, and it wouldn't really work. And back then those Solaris machines actually already had a lot of cores, So I guess I was really small kid back there, but I guess that was the main reason. The performance was the reason.
Yeah, true. Different time, different goals.
Yeah,
and
exactly.
different tools. Yeah, thank you. And the next one from Dmitro Malyon. Is there any unfinished work remaining around virtual threads in the GDK, or is it final? Any enhancements are planned?
I heard about some plans for the scheduler being more pluggable. I don't know. There are some sides, siding with no, we don't want that. We have to keep the control, and there are some sides which, yeah, we can do more magic with that. But you never know, right? It's because there is a really cool API hidden, which is not accessible, from the outside. And there is really cool API when you can actually manage those continuations yourself. They have API for themselves. It's really nice. So there are actually delimited continuations in JDK, which you can use manually, like you can do it in Go, right? So this is really cool, but it's all closed in, just for the reason, what if we want to do some cool tricks to make it even faster, but if we give out too much of the power to our users, it may happen, it will block us, because it's happened a lot of times in Java that some features kept it to be backward compatible. We couldn't really move forward. So that's one thing, I guess. This way, when it's not pluggable, it may happen that maybe we will have even the preemptive scheduling instead of this cooperative one. So who knows? Maybe we'll have even clever scheduler. I guess we will have it definitely. I'm just not sure if it will be pluggable or not. We will see. So there is a lot of room. There is great room for improvement. It's just it's those few super clever guys who will be meeting on the JVM Language Summit. I think it happens sometimes like next week or something. So I think they are streaming it on YouTube. So follow that. I guess if there is some news from those depths of JVM, you could hear that first there.
Yeah, probably most of interesting things might be hidden from us, but it's on purpose to do not shorten your leg. Yeah. And the last one, do virtual threads, also from Mr. Mike, do virtual threads remove the need for completable future, or do they work well together?
They do. It's just you don't need it that much. The thing is that completable future and completion stage, those are actually reactive operators hidden in JDK, right? That was before the Reactive Streams API. We had it in Java. It's actually quite powerful, but it's the same thing basically. You have operators. You have flat map. It's just called differently. You have on error, on complete, on you can cancel thing. I think it doesn't support back pressure. We have it, our reactive operators in Helidon, they can kind of like, you can switch between completable future API and reactive streams API, so you can seamlessly switch, but you lose the back pressure there because back pressure is not supported by completable feature. So those are actually kind of reactive operators. It's made to make async programming simpler. And if you are using virtual threads and structured concurrency, you won't need that anymore, right? So hopefully, like as a last resort, you can always use it, right? But you shouldn't need to.
Yeah, true. And this was the last question. Thanks a lot for answering and on these questions. And yeah, and my personal, I never tried Helidon, but after your presentation, would like to. Yeah, since it has first-class support of these virtual threads and a good API, so curious to try. Yeah, thank you for joining us today. Yeah, appreciate that. And yeah, have a good day.
Bye, everyone.
Bye-bye.